Hello, everyone, and welcome to the 9th lecture of the information visualization course titled Text Analytics. So today we're going to be talking about how to wrangle text data, which is a whole new kind of data with unique aspects that need to be taken into account. And we are going to do this chiefly through seeing some example systems and visual representations. So there has been a rather recent survey by Kucher and Collective in 2015 that have provided the first up-to-date complete taxonomy of text visualization and analytics. So we are going to go over this taxonomy to have a bit of a systematic approach towards unpacking what text analytics is all about. So starting with the data, text is a new variable type. So much like we had our nominal variables, our ordinal variables, and so forth. Text should be treated as a completely new variable type. It's a string of arbitrary length. So the string hello and the complete works of Charles Dickens are both examples of text data. The relation to categorical data, because there you might recall that categories are short strings. So how is that related to text data? Well, categories come from a pre-selected set, whereas text is completely free. You can write whatever you want, and you're going to have the text data. So you don't have the advantage of basically classifying with some kind of predefined labels. You just have free text, which can be anything and of arbitrary length. And the arbitrary length obviously presents a computational and visualization challenge, which we're going to go over. Note that text data, in addition to the atomic text variable, where you just have free text clumped up together, can be differently structured, which in turn drives visualization design. So that's this source branch of the taxonomy. So we can have a document, which is a coherent unit of text, also possibly structured into sections. It can even contain images. So that's one kind of basic structure unit. Then we have streams, which can be documents flowing in over time. A classic example of this is, for example, news data. So you have a new report coming in with a certain timestamp, and if you're trying to analyze some global event, such as possibly the 9/11 terrorist attacks, then the large volume of data flowing in over time is crucial to the analytics. And on the top level, we can have corpora. Singular of that is corpus. So those are collections of documents. So it's one aggregation level above. If we go beyond very trivial data, it's pretty much impossible to visualize raw text meaningfully, because a visualization of complex raw text is just read a book, right? If we really want to analyze text data in an efficient manner, we cannot just directly put it on the screen and make the user scroll. It needs to be processed into a meaningful representation that can then be visualized. And this is exactly the discipline of information retrieval and natural language processing, which is an open scientific challenge, and it's a very, very budding and vibrant research community. So of course I cannot attempt to summarize the complete works in this field in this one lecture. So the interested student should look at the Natural Language Toolkit, which is a very, very useful tool with nice tutorials. And I don't think that there is a very high entry barrier to just start using it. So the link is just nltk.org. I mean, there are also information retrieval courses given by the university by better experts than I am in information retrieval. So. But if you want to just process text data, if you just want to start doing some of those techniques that we're going to discover or we're going to talk about in this lecture, then NLTK is a nice tool for extracting useful representations. They have nice tutorials, and if you're a computer scientist, you shouldn't have big trouble accessing at least the basics, I would say. To give an example of an example data source that people can use, and indeed you can use too if you want to, is a news brief. It's a project by the European Union. There are news articles from over 2.5K sources coming in 42 languages. The sources are media portals, government websites, commercial news agencies. There is 80 to 100,000 articles per day, also enriched with metadata, and this is very relevant at all source levels, basically. So it's a big corpus. Articles flowing over time, so it's related to streaming, and the individual articles are obviously documents. So this is a nice source for text data that you might want to play with, and indeed it's a similar data source will be used by one of the systems that we're going to talk about later. If we go to the next branch of the taxonomy, it's domain. So text analytics is highly domain driven, right? So if you're reading any piece of text, it will require the knowledge in that domain. So if you read a text about astronomy, then it's good if you have some prior education in astronomy if you want to access advanced text. So not all documents are accessible to everyone, and this is of course reflected in text analytics as well. The knowledge domain also drives the conclusions from the text and does the insight. So the ultimate objective of visual analytics, right? And you should indeed reflect this in your visualization design. Which generally means do collaborate with the domain experts because they will have more knowledge than you. Regarding the analytic tasks, so what do we do with the data to A, as users, and B, to support users with our text analytics approach? Given that text is a very rich data resource, it comes with its own set of tasks. So, I mean, obviously, we still have the taxonomy by Pike that we have discussed in the interaction and evaluation lecture, but there's going to be some things on top. So the first one has a very lengthy name: text summarization / topic analysis / entity extraction. So what this means is those are various words. So for the same thing. So summarization means that you want to, if you have a lot of data and you want 1-2 sentences or maybe like a short description of what the text is about, for obvious reasons, that it kind of extracts the insights for you, and you don't have to read the entire text. The two key pieces for being able to do that are entity extraction, which is basically that you recognize which entities are present. So what actors the text is talking about. So I don't know, if you're mapping the US presidential elections, then your entities are going to be Joe Biden, Donald Trump, and you know, I don't know, the electoral college, maybe the voters in certain states. Those are going to be your entities. So those are the actors in your story, kind of. And I mean, you have to extract them from unlabeled text. You first have to discover what these entities are. And topic analysis modeling means that you establish relationships between them. So the topics. So what are they? How are they interacting? What are they doing basically within your domain? So that's the other part. So first you extract the actors, and you also extract their relationships or how they are acting towards each other, pretty much. It's basically this in information visualization, usually entities and topics, the boundaries are a bit blurred. So it's all treated as topics, basically. So these are all considered topics. So there's a bit of a discrepancy between the information visualization terminology and the information retrieval terminology, but yeah, it's good to be mindful of that. But I mean, if you just say topics, then it's all right. So Donald Trump can be both a topic and an entity, but you know, there is a bit should be distinguished for the purposes of the actual analysis, the representation mining rather. So that's what we discussed now is the main task. That's what many analytics systems are trying to accomplish. But there are of course other tasks. There's also a discourse analysis, which is the linguistic analysis of the flow of text or conversation transcript. Then we have sentiment analysis. That's another very popular task these days. From the words that are actually written in, especially like user comments or reviews, that we analyze the overall sentiment, or so is this a positive or a negative review? We also want to the more advanced approaches might want to detect opinion and maybe even affection. So that's a very commercially very popular tool these days. Then we have event analysis, which ties together with the geo and temporal lecture we have had last week. If we want to extract event, which are temporal data from text, then we might also need some text analytics tools because just to detect what were important events happening and how they influence our domain. Then we have trend analysis / pattern analysis. So we're just discovering patterns in the text data in the general abstract sense. Then we have lexical or syntactical analysis. This is analysis on the sentence structure level. So this is more like linguistics tasks. Then we have relation and connection analysis. So we compare data items, especially documents, including analysis of explicit relationships exposed by visualizations. So this is done generally on the corpus level if we want to compare and contrast documents. Maybe for plagiarism detection, that's one example of a domain where you need relation and connection analysis. And finally, we have translation and text alignment analysis. That's kind of self-defining, right? So we're translating between languages. That's simple, but also very needed. Simple concept, but rather still an open scientific challenge, of course, and a very needed application. Then we have our visualization tasks. So what can we do with visualization to help users analyze text data? So first we have the region of interest. So we are basically automatically highlighting, suggesting regions in the text that could be of interest to the user for more detailed investigation. So where the key parts of the action are actually happening. So sometimes text can be fluffy. This is very useful for especially. Or I could imagine this being useful for for law and legal applications, because I mean you have all these lengthy contracts and lengthy texts that describe usually a rather simple thing, but it has to be covered from all angles. So maybe like highlighting the meat of the contract, like where the real important part is, could be a very useful. For instance, then we have our classic triplet of clustering, classifications, and categorization. So of course we want to be automatically or semi-automatically tagging, labeling, and grouping data elements. Then we have comparison. So that we lay out several objects side by side and or mark discrepancy between various documents or pieces of text. Then we have overview. So that is providing the big picture by displaying a significant portion of the data, which is pretty much a synonym for aggregation. Then we have monitoring. So we are alerting users to changes in the data. Navigation exploration means that we need meaningful traversal of the data set, which will possibly involve switching visual representations of the underlying data types. So we might want to navigate to different parts of the collection. And I mean, explore is one of the key 7 interactions, if you recall that lecture. So in the domain of text and multimedia data, this needs to have semantic capabilities, so that you can say, okay, so I want to navigate from these articles about boats to articles about something that's about airplanes. So of course, first, to be able to do that, then you need to have an underlying representation that knows, okay, so this is talking about boats, this is talking about airplanes. And finally, we have the uncertainty tackling, which means handling or visualizing uncertainty in source or process data, as well as uncertainty in computation. So I mean, text is open to interpretation, right? So uncertainty tackling is one of the constituent disciplines, unsurprisingly. Regarding the visualization branch of the taxonomy, we know most of these techniques already, and we are going to discuss the rest today. So this is just a kind of a tick mark slide, so that we can move on. One that we don't really know is this one. It's called metric dependent alignment. So we have radial and linear parallel is what we have talked about during the graph lecture, right? That you can align graphs or trees in these kind of patterns. But metric dependent is new. And for text, this means that we have similarity-based methods on top of dimensionality-reduced data. So we establish similarity between the pieces of text or between the text items, and then we structure them, and then we project it using our favorite dimensionality reduction method to kind of see the overview picture of the text corpus. And you know, this is a bit of a spoiler. So you see that a lot of these terms have come in the previous lecture, which was graphs. So there's a lot of connection between the text data and graph data, as we're going to see in the future slides. Before we start delving into the visualizations proper, there's a great resource, again, linked to the lecture slides here. The authors of the taxonomy that we have just talked about have done a rather comprehensive survey of text visualizations in existence, also with links to papers. So you can inspire yourself on this website, and for filtering they use exactly the same taxonomy that we have just talked about. So if you know what I've been talking about in the last slides, then you can easily filter all of these visualizations. So there's 440 of them to kind of see what's in existence. We're going to cover some interesting example systems in this very lecture. But you know, of course, we're not going to go over all 440. So might be a nice idea to visit this site. Okay, so now if we want to see what some various text visualizations are or approaches for text analytics, as I said earlier, we're gonna this lecture is going to be a lot about examples. So we're going to go over a lot of examples, and we're going to see what's possible to do with text through them. And if you're interested in more details, well, you can of course ask me a question. That's always welcome. And the full details of their approach is always in the respective paper that we're gonna basically that's going to be mentioned on the slides. And I mean, all of those papers are optional reading for this course. So that's the way I've structured the text lecture. Okay, so first we're starting with line plot / river. So what does that mean? There's so we're going to introduce a new type of visualization, which is called a stream graph. It's gained quite significant traction since I think 2008, when there was a visualization of one of the first stream graph visualizations of movie sales in New York Times, and the graph became immensely popular. So we're gonna cover it. Stream graphs are a variation of stacked area chart, which itself could be viewed as in quotation mark a continuous stacked bar chart. So if you're gonna plot very thin bar charts for very short periods of time, they will kind of cover a small area, or maybe not so small, but they will cover an area. If you kind of plot basically time series as mini bar charts, or if you just draw the area under a line graph, if you plot the time series, that's called a stacked area. And if you stack them on top of each other, that's a stacked area chart. I don't think it's stacked area charts themselves are that useful, honestly. So that's why we haven't really covered them. But stream graphs are a bit optimized version of a stacked area chart, which is indeed popular. So we're going to cover that one. And our data, which in text are various topics. So we're going to have some volume of data on a certain topic, will flow through time in streams. So this data is not really text data, but to illustrate, this plot goes over the medal wins during Winter Olympics for various countries, and over time. So here we have the Winter Olympics, and this is just an illustration plot. So what it does. So the height of each of those streams is proportional to the size. So that's so you know, the thicker the stream, the more medals each of these countries have won, and the overall height shows overall volume and or seasonality. So we see that overall, from there have been way less medals being awarded in 1924 in Chamonix than there was in 2014 in Sochi. And what is a bit tricky about this plot is that the absolute positions on the y-axis are completely meaningless. So they are only optimized to be aesthetically pleasing. So all that is preserved is that these streams are proportional to the size, so you can compare with each other. But the way they flow kind of is it's a bit of a show off, you know. It's not like exactly analytical. It's optimized such that it will flow as a river, basically. That's as simple as that. And interaction, especially topical hierarchy and selecting relevant streams, is a must here. So this in static terms is not such a useful plot. We're going to see later that when you actually add interactions, there's going to be a couple of screenshots. It's slightly or not slightly, it's much better with interaction. The nice thing, actually the nice property about the y-axis being kind of meaningless in the absolute sense, or in the absolute positioning sense, is that this makes all these positions of these streams arbitrary. So you can reorder them, you can redraw them, you can highlight them, and you're not really changing the overall message of the plot, because you're not supposed to be reading values of the y-axis anyway. You're just comparing the streams in the relative sense. So there is actually an advantage of sorts. Here we have some kind of basic example of a stream graph, now including topics based on two levels of abstraction. So we're gonna go over the example of people listening to various styles of music. So here we have metal over the years. So in A we can see the overall pattern that it was declining from 98 to 2001 slightly. Then there was a boom in 2003, and the overall volume increased compared to the 90s, even though it kind of waxed and waned a bit. And here there's the topical decomposition. So you can say, okay, give me one level of topical hierarchy lower, and here we see streams for alternative metal, power metal, doom metal, and black metal. So you can go, you can kind of change the levels of abstraction, and explore a bit more in detail. So I mean, this flows from the observation that the topics, if you extract topics, you can extract them at various levels of abstraction. So you have music, then you have metal, then you have power metal, and then maybe there are even some subfields of these little or these smaller streams. And that's also why text analytics is so related to visualizing graphs, right? So if you have topic hierarchies, then topic hierarchy is a tree. So then you visualize it as such. So it's a bit of the boundary is a bit fuzzy there.
Like 2 more minutes, by the way.
Okay. So it's actually a good idea to stop here. Are there any questions?
Yeah. Yeah. Thijs asks, it seems that visually the width of a horizontal stream looks wider than the width of a diagonal stream. Is that a problem?
Okay, let's go. So I'm not sure I understand the question exactly. So width of the horizontal stream width of a diagonal. So you mean that here it looks different than here? Is that the correct interpretation of your question?
I'm not sure. Isn't typing? Here's only one Thijs in the Zoom call. So
okay. So if I misunderstood it, then please feel free to jump in also in voice and correct me. But I mean, I think so. So me personally, I am not a big fan of stream graphs. I do think that yes. So if you look at it like this and you look at it like this, then it is a bit difficult. But that's the price you pay for this visual optimization. I'd say. So again, I'm not the pioneer of stream graphs. I generally would avoid them. I'd guess myself, but they have gained a lot of traction in the state of the art, and people are using them. So that's why they have a right to be taught in our course. Yeah, I'm not sure. I would be hypothesizing when it comes to answering this question. So I don't have a defense for stream graphs in this regard. But yeah, you make a good point. Yeah, if you when it starts to turn upwards, then you might have a bit of a different perception. But you know, I'm not sure I can answer this question convincingly, honestly. The idea is that you have your time data and you use an algorithm those are usually published in a paper, and that it will do this pretty much. So, but this reason it's a good thing. I'm going to try to find more information about this, and if I do, I'll let you know on Discord. Let's see.
all right, thanks. Then Ahmed asked, so stream graphs is more about relative weights rather than absolute values.
Correct. Yes. So it's all about being able to compare things to each other. So here, if you want to go over a couple of insights, there was like a big boom of East Germany medals from 64 to well 92, which is not surprising, because then East Germany unified with Germany, right? So the trend that you're looking for is that, wow, East Germany has really sprung in medals in this time, you know. So yeah, so indeed, it's all about the relative comparisons. Yes. Any other questions?
Okay. Yes. Then Kalle asks on slide 21.
Okay.
Would you label the near lines? Would labels near the lines be preferred, or would it be better to give each line a different color and then explain the colors in a legend?
It would be very preferable indeed. So this is just the kind of the blueprint / technical drawing, which is basically. So we're going to go over this this multi-stream paper, and here already on this slide you see that it's doing exactly. It's way clearer. So yes, you're absolutely supposed to use colors. But this is I wanted to start with the kind of technical drawing, and then we kind of went for a break. But this is absolutely the way you should do it in your final visualization.
All right, I think that's it for questions for now.
Very good. So let's take a 5-minute break, and I'm going to see you again at 34 then. All right, so let's continue. We've been talking about the text analytics taxonomy, and we have started with the example systems. We've discovered the stream graph, and I realized that I have ended the did the first section with basically exactly before when it starts coming together. So let's start the next part exactly with that. So what you can actually do with stream graphs is what's called a multi-resolution view. So you can have because it's very nice. It's very nice for the visualizing the topic development over time on multiple levels of the topic hierarchy. So in the A areas we see the two top topics. So it's like it's top level topics rather. So that you have jazz, you have metal, and because we're using the river / stream metaphor, we are. You can split the rivers, split the streams into multiple topics, and then you can merge them back together. Similarly for metal. So this is the right correct way to do this. So you can see how your how the listening to various genres of music flows over time, and it's smooth. It's nice to look at, and the splitting and merging of the streams is a bit more fluid, smooth, continuous than if you would have node link diagrams. So that's an argument that you could make for a stream graph on the cognitive and perceptive front, because I mean that's one of the Gestalt laws, right? The smoothness, so that we tend to prefer things that are smooth. So you can do this multi-resolution view. And yes, we're going to be talking about a system called Multistream, which is from 2018. A nice thing what you can do here is that you can use fisheye / lens tool to transition. So instead of having this split at predetermined intervals, because this is going to be your timeline, right? So on the x-axis you're going to have your timeline. So imagine that this red dot would be a lens. So if I would go here, then it will basically it will create this level overview as I go over time, which is very powerful for the powerful, like, abstract, elaborate interaction implementation. And going a bit behind the interaction, so here we have this visualized more explicitly. So as I said, text analytics highly related to graph visualizations, because this would be our topical tree. This is the root, music genres, and then we have rhythm music, rock music, pop music, and so forth, going all the way to the leaf level genres. And this is our visualization, our stream graph visualization, and here we have the overall timeline below, and you can see that we can distort the stream graph a bit to really highlight the period we're looking for. So here you see that the x-axis doesn't progress in a linear manner, and this you can set yourself with the sliders here. So that's quite a nice tool. So we have discussed that using nonlinear scales could be unintuitive. Well, yes, that remains the case, but this allows you to set it yourself. So that as the intuition, if you set it yourself, then it's automatically intuitive for you, right? So this allows us to really see in detail how people were listening to music in around the year 1989 in this case. A bit more about this topical tree. So it's a time series hierarchy in a tree layout. The vertical dotted line show levels of abstraction. The authors of the paper use the word high level abstraction or context areas for the blue connected levels, and for the green connected levels, those are the detail areas. So they say context, detail. So context, you see the overview; detail, you see the detail simply. And you can clicking on the tree, you can aggregate and disaggregate. So this is kind of the fisheye lens. So this one stays the same detail. But for the first section of the graph, by clicking here, it will jump to the next level, and this will get broken down into the three style genres, one level below, and aggregation goes the other way. So if you click here, then it will jump back to here. So metal will get aggregated back, but only metal. So from here you're jumping to all three, but here, because we were in the metal subtree, then we're jumping only back for metal. So here we see this kind of jagged line. So it will not jump again. So clicking back on black metal will not aggregate the punk styles, because that will require explicit interaction. Also, another very important interaction is highlighting, which can be viewed as an example of the select interaction. If we point on nodes, we say, okay, we want to see reggae. It will simply highlight the reggae stream itself, because it's a leaf level topical node. Whereas if we hover over electronica, it's in the context level. So all children of electronica are going to be highlighted, as we see on the example below. And they have also done, like as a case study, they have done sentiments in tweets after the 2016 US presidential elections. Here, I'll admit that I forgot which one is which. So one of these is Hillary. One of these is or tweets about Hillary. Tweets about Trump. But I'm not sure which one is which now. So sorry about that. But why I actually included this in the first place was this one, where you can see that. If you remember when we were talking about stacked bar charts, we emphasized the need for being able to put the bars on the baseline any way we please. So they have actually added this interaction to the stream graph. So this doesn't look really like streams anymore. So if you would have water flowing from left to the right, so this is a very dramatic way to do this. But this is again more analytic. So they have aligned the baseline. So suddenly making these y values matter. So I think that this is actually a very very powerful analytic interaction. So even though stream graphs by default don't have this y-axis meaningfulness, you can still, with interaction, you can still introduce this. You can allow the user to rearrange it and view it in the more kind of analytic / classic visualization sense, which could be very useful. So I think this is a very good compromise between the two forms.
We have a question from Ahmed. He asks,
okay.
in the tree layout, the absolute values can be added for selected time. Is that correct?
So yeah, yes, that definitely would be an extension that I could see as useful. I think that one of the reasons why it hasn't been done is that we're going to see. I think there's going to be a slide about the final way this. Did we actually see this already? Yes. So if this is the overall dashboard, then having numbers here could clutter the detail, right? So if you have this on the screen, there is already a lot of information to go through. So I think for the sake of brevity, the authors have opted to just show the names. But you are absolutely right that this could be added to the screen if this wouldn't overload the user. Or alternatively, what you could do is that you could have like a button here or something like that would say just show frequency or show count, and that this would get re-encoded with a single color by intensity, and it will kind of like show the relation. So that could be extensions of this approach. So it's not wrong. I think that here they have opted for the simple approach due to possible clutter. Yes.
All right. Thanks. I think, yeah, we can continue.
Okay, perfect. Right. So this has been the multi-stream system. So that's a way to do these stream graphs, which are called line plot / river. I mean, to those interested of you, why it's actually called a river here and not a stream graph. The reason is that I think that it was originally called theme river or something like that, but the authors have registered this as a trademark. So so of course the community looks for something that everybody could use without having to pay money to the authors. So so that's how the term stream graph came to existence, I believe. But it's the same thing. So that's what we meant by line plot and river. Pixel area matrix, we've been over these matrices, adjacency matrices yesterday. Node link. So we have, sorry, the last time. And node link, we have been over that last time as well, but still it's nice to see the explicit relation to text analysis. So an example of a system like this, and this is one of the examples because I think this is by far the most used paradigm if you go over text analytics papers, is that you model interesting things in text as nodes of a graph, and then you just plot it, treat it as a graph visualization henceforth. So here, this is a system called Story Tracker, and yeah, so their data is very similar to the EU news brief that we discussed in the beginning of the lecture, right? So we have news articles flowing in from multiple agencies at the same time. So there's a rather large volume of data coming in every day, and we want to detect what kind of important stories there are for certain topics. So we are going to want to track the stories. That's directly in the name of the system, right? So what we are going to do is that we're going to and this is the slide showing the explicit relation between topics extracted from text and the graphs, is that we have our topics follow a hierarchy which can be split into multiple subtopics or merged back into the super topic. And here, what we see here, this is a bit of a lengthy. This is like an overview, topic overview. Is that each of these rectangles is a topic. It flows over time. So this is our X is our timeline. This is the abstract form of the visualization. We're going to go over more detail, of course. And our topics are flow over time. So this one flows here and then it stops, but this one flows and keeps flowing up all the way up to here. And we have multiple of these topics that persist over several days. So each of these columns is one day, and we have we introduce edges to show that a topic has been talked about for multiple days, and the height of each of those rectangles is the volume. So how much in total relative to the other key topics has this one been talked about. To reduce the clutter, because I mean, if we would do this for all the news from all around the world, it would be a crazy cluttered visualization. We only we have two filters. One is connectivity, the other is duration. The connectivity filter means that only similar stories are going to be shown, and which requires semantic analytics of the semantic analysis of the text, or semantic representation of the text rather. And then we also have the duration filter. So we only show stories that develop over a certain period of time. So what could be useful here, for instance, is to cut all the stories that only show up for one day, right? So those are the filters that are there in addition to filters such as the total volume. So of course trivial stories that have been mentioned once by some obscure news agency, those are not being showed at all. That's kind of an implicit filter, right? And of course, the visualization is arranged such that edge crossings are minimized. So you could because the ordering on these columns is arbitrary. So you select an ordering such that you don't go over each other. You don't cross too many of those edges with each other, because that leads to a clutter or confusing display. there's details on demand. So here we see one of the streams, and by interaction you can look at the story in more detail, and you can even, like, there's even a tooltip where you have maybe some multimedia associated with the news. You have a summary of key actors, and you can read the story on demand if you deem it relevant to you. And the case study where the Egyptian riots and unrest in 2011, and yeah, so I'm gonna go back. I thought I had it here. So, and this is the default view, by the way. So I should have elaborated. I thought I had it once again at the end. So this is how it will look mostly. So we see William Hague being talked about here, and not so much here. And you also see some key topics or keywords extracted from these stories to give you a bit more context about. Okay, so we're talking about William Hague. So, but why? So why do we talk about William Hague, right? So you need a bit more details on that. So this is one of the earlier approaches that really went into some serious text analytics, combined basically visual analytics for text. Yes. Okay. Going further. Other visualizations we might encounter, and we encounter them a lot, are clouds / galaxies. So what is it? So you have probably all seen a word or a tag cloud. It's a very classic tool to summarize text. You just count the words in your text corpus, and the word sizes are proportional to their frequency. So the number of times they occur in the corpus. And colors can be used to either encode categories or to enhance the frequencies. So we see the latter case in this visualization. So we see one color hue and different intensities. So the more prominent or the darker the intensity, the more prominent the word. So it's a bit of an additional visual cue for in addition to the size, the prominence of that word. So, and actually the same thing applies here to as when we're talking about choropleths. So if you're trying to enhance frequency, then use one color hue and just vary the brightness / intensity. And if you want to encode categories, then you use different color hues. It's actually the same principle now that I think about it. So what's the problem with the word tag cloud? So is this the way to do this? So the problem is that the classic inline word clouds, as we see here, are quite screen space inefficient, because there's a lot of white space. So for example, if we say here, so everything is on one line, and we see that there is a lot of screen space wasted if you have small words in the middle of bigger ones. So can we do better than this, right? An additional challenge about this is the word frequency distribution. So the tendency is that if you take a text corpus in general and you count the frequencies of words, you will very often have what is called long tail distribution. So you will have few words that dominate the count, but there's actually going to be a lot of words with small counts that are possibly interesting. So they're going to form the long tail, speaking statistically. So what this means for a visualization, we have to be really careful when we're choosing the scaling when placing the words in the cloud. Because if we are not careful about this, then we're going to visually drown out a lot of the data with the top small percentage of popular ones. The general rule of thumb, or like the practical guideline, is that if the distribution of is power law or power law-ish, which it usually is, I mean, it's roughly similar to that. Then if we do logarithmic or square root scale, then it will generally work fine. So we're not. So if we are converting the count to pixels, then we're not going to do this linearly or even polynomially, because then we're going to even highlight the differences. But we're gonna scale it logarithmically and with square root, so that will smooth the kind of jagged differences between the words. That's a way to do this, but it still remains a challenge. So the most common technique for doing word clouds or tag clouds is called Wordle. It's used to this very day. It's basically a more screen space efficient cloud. It's very related to the scheduling task of bin packing. It's a constraint satisfaction problem. So you have a bin, and you have various items that you need to place in the bin, and you of course want to be as efficient with your bin placements as possible. I mean, you can see the obvious industrial applications of this constraint satisfaction problem. And this is basically the way you can. So if you go with the largest size first approach, then this one will not get fit. Largest size first is again, this one doesn't fit, and there's this thing that you can also download. It's called Rules Planner, which will be able to fit this all very nicely. So it used to be called Rules Planner. Now it's called named Opta Planner, but it's to the best of my knowledge is the same thing. So if you're interested in this problem, then you can, for example, go with Opta Planner. Maybe there are others. I'm not in the scheduling research area, so I'm not sure what the total state of the art is, but this works fine. Basically, so we're doing this bin packing, and given a list of words with weights. So we have our words that we want to display, and we have the weights, which are generally the frequencies. There can be other methods to do this, but the basic one is the word frequency. The rule is that you shouldn't show words more than once. So each word should be encoded exactly once. And you shouldn't distort the word shape. So the font. So if you have the font, you shouldn't stretch it horizontally, vertically, or horizontally. I mean, rules are sometimes meant to be broken, right? And breaking these rules creatively can sometimes be beneficial. Like, for example, this is a more of an image, more of an artistic thing. So I'm not sure this is very analytically useful, but it's kind of cool, right? And I mean, here we see that the word evil is being plotted more times, such the Jedi as well. And so we're breaking the rules of show everything exactly once. And a more analytic way to break these rules is that if you distort the font, you can possibly create a tree map. So this visualization is actually a tree map. I'm not sure. I have found this as an example. So I'm not exactly sure about the underlying corpus, but we have seen tree maps in the graph lecture last week. So this is a bit of a analytic way to break the rules a bit. But now let's assume that we're following the rules and let's continue with the Wordle algorithm. So the algorithm pipeline, again, in a high level overview sense, is that we have our raw text. We're going to perform text analysis. So we're going to do this find a useful representation, detecting entities, detecting topics, and whatnot. So we're gonna have to process the text, and then we're gonna iterate over the word placement, bearing in mind the layout constraints, which get updated with each of these iterations until we arrive at our final Wordle. So regarding the text analysis, a bit in detail, a bit more light about the techniques that are employed in the processing sense. And NLTK, the recommended toolkit, will do all of these things for you if you actually call the proper method. So you don't have to do this by hand. So we're gonna have to find words. So we have to be careful about what a word really means, because sometimes for some languages it's very important to have stemming. So because they vary the prefixes and suffixes of words quite often, but it's the same word, right? In the semantic sense or in the meaning sense. So, you know, with your language, be careful what a word really means. Sometimes you have phrase verbs for like in English. So if you put up with something, then you shouldn't be splitting this into two words, put and up, right? So finding words sounds trivial, right? So just break it down by the spaces, but you know, this in itself contains a lot of challenges for many, or virtually for all languages. Then we're also, for the visualization sake, we're determining the appropriate font. So we have to make sure that all letters are readable in the cloud. I mean, this is one step that NLTK will not do for you, of course. This is part of the design that you're opting for. Then we have to go through the motions when it comes to the language of the text and the so-called stop words. So we detect the language, and as a consequence, we remove words such as like, if we have in English text, words like the, a, and are very frequent, but they carry no meaning on their own. So if you would just take raw text and you would just directly draw a tag cloud, and you would do this for the English text, then you will have a huge the, a huge a, huge and you're going to have like some small things on the bottom. So you absolutely need to do the stop word analysis. And
yeah, just like 2 more minutes.
Okay. And finally, you have to assign weights. So each word has to have a weight, which then determines the proportion of the size it occupies on the screen. So yeah, you just use the frequency. So simply counting the words is a good start. It works reasonably well, actually. But I mean, we can consider many other variants. So another one, which is, again, at this time in information retrieval, it's a classic, but it will change things. It could change things considerably. If you have TF-IDF, then you are weighting words by their frequency and also rarity. So words that are frequent, but they are frequent in all documents equally, are penalized compared to words which occur in certain documents, but not in others, or they are a bit more rare. So there are other things to consider than just the word count, right? But you know, counting the words is a good start. TF-IDF is one step beyond, and there are, of course, many other elaborate methods in the domain of information retrieval. Okay, so let's pause here. Are there any questions?
No, for the moment, there are no questions.
Okay, so a 5-minute break. I'm going to see you at 07 then. Okay, let's resume. Were there any questions during the break?
No, there were no further questions in the break for now.
Okay, so we'll keep going. We have started discussing the Wordle algorithm with the first building block, which was text analysis. Moving on, one of the components is also layout constraints, which is basically that we have to determine the playing field, so the total area of boxes, the aspect ratio, and some amount of slack space, of course, because we're not filling the space fully to the brim. And these layout constraints are going to be updated as we start placing words. So if we place the first words, then we will start running out of space and so forth. And regarding the word placement, so how do we actually place the words on the screen? Usually the algorithm is the randomized greedy algorithm. So we place elements one at a time, and when an element is placed, we don't change its position, or we employ something more advanced, so a constraint satisfaction problem planner. So our algorithm is a choice, of course, and you know, there are usually ready-made algorithms to use. But it's very useful if we determine where words want to go, basically. So is there an overall layout that that we want to impose, if possible, on the words when they actually get placed on the screen. So, for instance, we might want to have them sorted alphabetically-ish to place them near the horizontal baseline, maybe. Or we can employ some semantic clustering. So we want words with related or similar meanings to go together. So when we place a certain word and we find another that is related to it, then we are gonna attempt at placing it to the same location. So and this is up to you. This is an extra thing to take into consider before we start running our randomized greedy algorithm or our CSP planner. Because those would be, for example, for the CSP planners, those would be additional constraints. So an example of a Wordle, I think this is a Wordle of the United States Constitution. Here we see an example of placement on a spiral, so we see how they alternate the horizontal and vertical placements to kind of utilize the space and spiral out of this spot. Here, if I would criticize something, it would be the arbitrary use of colors. So we see that I don't think there's a good way to do it. It doesn't really show categories. So Horatio, May, Father, Die is purple. Hamlet, like, speak, let is blue. I don't think, I think the colors are a bit arbitrary, but yeah, but it's meant more as a positive example, as you kind of spiral out of to show the spiral layout of Wordle, which is also possible. Now, okay, so we have all these tag clouds and everything, but is it actually good in InfoVis, right? They are widely used, so I mean they have stood the test of time. They are used in practice, but if we look at it in a bit more detail, so the good thing is that they are screen space efficient, especially Wordles. They allow for summarization, so if done right, you can kind of see what the text corpus or the document is about, and they are or can be aesthetically pleasing. All of that's good, but there are a couple of caveats. Long words may get overemphasized because they will obviously occupy a greater horizontal space. Or I mean, if they are shifted 90 degrees than vertical space. But word length is not necessarily proportional to interestingness, right? So it's a bit of an arbitrary dimension, so to say. I mean, it's not exactly arbitrary, because in most languages in the world, the length is actually proportional to the frequency. So the words that are used often are shorter. But it doesn't have to be proportional to the interestingness and importance in the certain context that we want to show in our visualization. So this needs to be taken into account. Color is often arbitrary, as we have seen in the example on the previous slide, for instance. But as we discussed, a better InfoVis practice is to, if we're using them, let's use them properly. Encode categories if it's meaningful to encode categories in the word cloud. And again, use various hues for your various categories. If we want to emphasize the frequency, then we vary intensity. And all in all, word clouds are just a quick summary, basically. So you should be treated as such. So they can be powerful. It's a very nice technique, but in certain contexts, they have been touted as the be-all end-all text visualization, but they're not that. So it's one of the techniques in the toolbox and should be treated as such. And analytically, the graph-based visualizations that leverage the topical hierarchy are usually way better. So in the general sense, so it's a useful tool. Use it wisely. And we have talked about clouds and galaxies. So what does the galaxy visualization mean? Galaxy basically means that we combine the word cloud with a graph. So that's kind kind of offsetting the disadvantage of the cloud visualization. And an example system that we're going to be discussing here is called Topic Panorama. I think I have showed it a couple of times before. So what's this about? So we have topics that are being discussed on various popular popular sites. I think it's even by the search engines. So we have Google, we have Microsoft, Bing then, and Yahoo. And here we see kind of a graph-based visualization of various topics, and we're gonna see some clouds here as well. So let's delve into this. So we are actually analyzing topics from different sources: the news blogs and microblogs, accessible from these three search providers. And again, we have a combined corpora plus streaming plus document level, because again it's news and it's a large volume of that, and for the same reasons that we have mentioned with some of the previous approaches. So to give you an overview, so here we see the three providers as a so Google, Microsoft, and Yahoo, and we have some of those key topics that are discussed on various ones in certain time, right? So we have topic words again by color coded by the provider. So the topic words is actually a cloud visualization, and we see multi-view design with the graph taking the main portion of the screen, and we have some details on demand here, and it kind of shows different levels of aggregation. So this is actually a summarization view. This is a detail view, right? So we see the actual topic documents, again color coded by the provider. And here is a nice visual decomposition of how we can arrive at a visualization like this. So we see that we create topic graphs for each of those providers separately. Then we branch out. So first we build a topic, or in one branch rather, not necessarily first, we build a topic hierarchy. So that gives us this nice kind of compound graph leverage, and we can start zooming in and out. And also in the other branch we do graph matching. So of course there's going to be topics talked about by multiple sources, or like accessible from all three providers. So we need to match them together so that we don't have, you know, Barack Obama Google, Barack Obama Microsoft, and Barack Obama Yahoo. Of course, it's the same entity, right? And when we have this, then we can visualize it. So this is basically the model in the visual analytics sense. And yeah, here this is a bit more detailed. What I have just talked about. So basically we have interaction plus different levels of details with also this slightly cheesy clip art. But yeah, so we visualize everything and then combine. This is basically our Galaxy plus also a bit of a timeline for the total volume per provider. Yeah, again, this is the diagram of the node layout. So this is just a bit of a blueprint. How do we lay the nodes out in the radial visualization? I don't think it needs total decomposition. So, but basically we start with this in the respective region. So corpus C starts in the green one, corpus B in the orange one, and corpus A in the blue one. And then you're using this force-based layout to kind of if multiple talk about the same thing, then you want to use these springs and masses to like especially pull the ones that are talked about by all of them to the center, and 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 pull those that are being talked about, I don't know, by corpus C, and then those are going to be near the kind of the corpus C region. And we also see that this is a Voronoi diagram, right? So it starts as this. So this is the original layout. So you have these various regions. So this is the only blue region. This is the blue plus green region. This is the only green region. This is all of them, and so forth. And basically, when you actually pour in the data, then the Voronoi diagram, or which gives the kind of the jurisdiction of each of those focusing points, is updated based on the volume of data in each of these respective regions. So it gets from this perfectly regular shape, it gets recomputed accordingly, basically. And here, when you see it in more detail, so each of those nodes is the so-called representative node of a topic that is important. The node link diagram is using force-based layout, which we just talked about right now. So the topics are pulling each other and repulsing each other. This is basically like a based on the radial icicle plot. That's how you kind of start setting things up and then start pulling them together. If you look closely, each of those glyphs is a mini pie chart, and it will indicate topic share by media. So this one is that everybody talks about this. This is only talked about by the green one. This is so by Yahoo. This is only talked about by Google and Yahoo, and similarly to the others. It appears here that these are just glyphs, so all of these seem to be exactly the same. So I don't think that these are actually proper pie charts, in the sense that they give you the exact share between the three providers. So they are all equal. So I doubt that all have been talked about exactly equally and exactly proportionally. So 1/3 by everyone. But it's still a visual representation that this is a shared topic. So a possible extension would be that you actually plot the proper pie charts there. But this also serves its functionality. So it gives you a nice categorization, nice overview. And this is a bit of a exploration possibility. So what you can do, I'm actually not sure what this does. Yeah, I'm actually not I can't remember what this does. I'm sorry. I should probably add a caption here after the lecture. Excuse me. Yeah, but and the best is that you can easily access a demo video, so it's always best to see things in action. So if you're interested in how Topic Panorama works, or it's possibly relevant to your own projects, then feel free to see the demo video. Going further, we have the maps. And an interesting approach that we want to include here is so-called event queuing. So this is the overall dashboard, which is a bit confusing at this moment, but we're going to see it in detail and then kind of piece it back together. So event queuing, what's that? So we have talked about event detection being an important part of text analytics, and we want to gain insight into events through analysis of online news, microblogs, and also other media. And usually whenever something happens, we have various competing points of view that can often take over the discourse, and this is what is called framing. So the term they use for this is framing, that the communicators of the information form a point of view that encourages a certain interpretation of events, and they do it either consciously or subconsciously. Sometimes they do this analytically or in a let's say objective manner. Sometimes they do this maliciously, but whatever the intent may be, or lack of intent for that matter, it's useful to be able to analyze this, right? So what we need to employ is we need to employ pattern analysis to determine the spatial distribution of frames to analyze the international context. So the pattern analysis here is basically various frames and pieces, news pieces coming in from various parts of the world. Then we have event analysis. So that's the temporal focused analysis. We want to analyze the key events that happened in time and how they influenced the framing of the event. And of course, entity extraction. So we want to identify the key actors and pieces in the discourse, who and what these are. So how can analytics help us with that? So now let's go over the constituent components of the pipeline. So the maps. I mean, why this was categorized under maps. So of course the choropleth is if we're trying to see the international context, the spatial kind of pattern analysis, then a map is a very good visualization for that. There can be three forms, or there are actually three forms in this approach. One is that you just have a choropleth of where countries are colored based on frame density. So how many frames came from this country? So we see that Nigeria seems to be active in this particular, Nigeria and Kenya. Then we have a so-called cluster pies. So we have various frame categories, which we're going to go over in a minute for this approach. And the pie chart will show the proportion between various frame categories. So we can see how different countries are contributing, or news from different countries are contributing to individual frames, which is useful to kind of see the overall intention. And then we have this hybrid so-called weighted category choropleth, where countries are colored by those frame categories that we see here, and they are based on the user input weight. So you punch in which ones are important to you, and then it will try to determine the dominant color based on your weights, basically. So if you want to suppress or highlight a certain part, then you certainly can. An additional component here is the so-called lens-based visualization. So you have your lens under your cursor, and you can hover over the map and uncover different things. So here we see that in the left mode, we see the most frequent text entities in the lens area. So basically, we if we go over Nigeria, we summarize all text coming from that country, and here we have maybe a word cloud based visualization of what the detected entities from the text there were. The central mode, like the B mode, is in the middle, is the actual actors from reference curated data set about the event. So this task that they have done, where some riots in Central Africa, and there was a curated data set by political scientists, historians that kind of established the so-called the ground truth, like what actually happened there. So like using the historical / political science methodology to be neutral and to be unbiased, to give good report, basically. So and this was considered as the ground truth. So this kind of curated data set was the ground truth. So what we see here are the actual actors from the reference curated data set. And on the right, we see a combined lens. So these are the entities, and these are the actors. So you can compare whether the entities match the actors. Another important part of this is called the Bda analysis, where Bda stands for before, during, and after. Basically, for each evaluated time frame, they are comparing. So that's part of the temporal analysis. They are comparing the frequency trends for frames, entities, and actors in basically these three stages of an event. So if an event happens, then they are comparing if the frequency increased, if it decreased, or if it was oscillating. Basically, they are color coding it by three different shades, and the significance is determined very hard by statistical tests. So they are doing statistical tests to establish whether there was an increase or decrease. So it's a bit more robust from various sources. And if you think about it, then this BD.
Oh, sorry. 2 more minutes. I just want to say.
No, okay, thank you. This enables the temporal data abstractions technique. So what we have discussed in the temporal geo and temporal data lecture, that if we're looking at some time series, we really want to see identify the key kind of intervals of our observed variables. So is this a high value, medium value, low value? We want to see the gradient. Are we increasing or decreasing, which is exactly this, right? And also the rate with which this is increasing or decreasing. This is fixed, but the rate is basically if it's supported by statistical tests. That's the kind of strongest indication there is that there indeed has been a significant increase or decrease. So the rate is fixed. It's significant, statistically significant, but that's well, significant. So it nicely enables temporal data abstraction, and that allows us to reason about the temporal developments way better. We can take a pause here. And are there any questions?
No, I don't see any questions in the chat.
Very good. So I'm going to see you at 35. Okay, so we can continue unless there were any questions during the break.
No.
Okay, perfect. So we've been talking about this event queuing. How do we analyze the discourse influences on certain events that have happened in the news? And we have been discussing the Bda analysis, so before, during, after, and this is an example of this hierarchical frame exploration, which does use this type of analysis. So here we see the frame tree, so all frames, then the cause. It's I'll admit that the frames are a bit abstract, so that the cause, maybe that there's been human causes, natural causes, uncertainty causes, policy causes, and I don't know what insufficient cause here means, but they are a bit abstract. But treat this as these are aggregations, and these are the leaves are various explanations or various proposed explanations for why certain events have taken place. And our timeline here is enhanced with the Bda analysis. So as we discussed, then if we see a significant increase, the window is color coded blue, decrease green, and oscillating orange. Slightly strange choice of color palette, if you ask me, but this is what they have used. So let's roll with this. So here we see that the human cause thing has been oscillating quite a lot. Here it increased. Here it was oscillating again. So different shades of these colors are basically different types of increases, decreases, and oscillations, right? So here you see that it can be oscillating like this, or it can be oscillating like this. Increase and decrease is similar. So different shades of green and different shades of orange and blue are there to reflect the different patterns that you might see. But it's for the sake of simplicity, let's focus on just the basic hues. So we see a lot of oscillation in the human cause explanation here. And whereas here with the policy, we see that around October 12, it was increasing steadily, and then it was consistently decreasing towards October 19. So each of these windows is one day, and we can analyze different patterns of the frames or of the explanations for the events that were proposed by the various sources in the international context. So I think this is actually quite a nice way to do this. Again, my one criticism would be that the color palette is a bit weird. I might do green for increase, red for decrease, and yellow or something, or orange for oscillations. But you know, this was their choice. So let's respect that. I think this is still a powerful way to do analytics on events. And of course, I mean, we're in the text analytics lecture, so text visualizations are important here as well. So indeed, they are using a Wordle style display as one of the side views, and also like a detailed view in list-based summary. So this is just the aggregate of the topics that you can kind of see on demand. So what the news reports were actually writing about, and this is the summary. I commend the correct categorical usage of colors in the Wordles. So here you see that people are color coded red, organized locations are color coded green, and organizations are color coded blue. So this is nice. So you can see that this was talking a lot about locations, about some key people. This is done right in this approach. And this is the full. This is again the full timeline. So we can examine the map. We can do our Bda analysis with the frame tree. Here you can actually see the different shades for the patterns that emerge. So here it's a bit more in detail. So different shades. This is just a pie chart, so that we didn't have to go over detail here. And together, when you actually unpack these individual components, then you can see it's a kind of a powerful dashboard. So the final approach I would like to discuss today is called Concept Vector from 2018, and this is an example of a visual analytics tool to construct a good textual representation. So we have talked about text representation being generally extracted by automatic tools, which is the state of the art in many disciplines, including information retrieval. But there might be a case for collaborative process between a human and a machine, as we see, and this is exactly the domain of analytics, right? So concepts in this context means a set of semantically related keywords describing a particular object, phenomenon, or theme. So basically our entity or our topic. So this is the definition that the authors use, but basically semantically related keywords to a topic or an entity. To those of you that have studied computer vision a bit, please be careful not to confuse the word concept with what it means in computer vision. It's a bit of a different word. And this is the overall pipeline of the concept vector system. But the key thing is that it's indeed a collaborative process between a human and a machine. So to give you a reason to do this collaboratively. So say that we have tweets by the 2016 US presidential election candidates, and for each of them, basically, so we have clumped all the tweets together, they have clumped all the tweets together, and they have run an automatic topic extraction algorithm. So for Trump, they have detected ugliness, swearing terms, surprise, beauty, plant, fire, and so forth. For Clinton, they have children, anger, disgust, joy, health, youth, and so forth. So sounds good. We even have this nice histograms. So we're cooking, right? But if you actually do the same plot, but if with the bars are depicting the frequency of words that led to the categorization, so why does the automatic algorithm believe that this is the right topic? Then you actually see that there is a lot of topic, especially on Trump's side, that are kind of misassigned, right? So for example, it has assigned the plant, but the key word to support the plant was actually Bush, which was highly probably the former U.S. president rather than than an actual type of plant, right? And there are like crooked. So you might remember that he was using or even overusing the term crooked Hillary. But he didn't mean that she was ugly, right? He was hinting, he was alleging some lack of moral qualities rather than physical ugliness. So there is a bit of a problem with these automatic topics, and I think this is a very simple yet a very powerful visualization of the limitations of automatic techniques. Basically here, another example. We have tweets by companies in the NASDAQ 100 list, so the 100 biggest or powerful influential companies. We have established a word count for 194 concepts, and then we have we can cluster it by using k-means, and then we can PCA project it to 2D. Or I mean, that's what, again, I'm saying we, but that's what they did. I had no part in this work. So if you do this just by automatically extracting the topics, and you just kind of project everything, then you will end up with something like this. So you're going to have a huge cluster here, and you're going to have a couple of outliers around that, which is not ideal, right? So it's not, because it's not discriminative. Because if you say, okay, so I have my wonderful clusters, and the clusters are that everything is together, everything is one cluster, then it's a bad representation like this. And it's based on very trivial relationships in quotation marks, because the companies that have are clumped together because they have technology in their names, right? Which is very vague. That's not saying much about the actual business. And the reason why this is an outlier is because of the actual word dish in the name of the corporation, but it's also a technology company, so it should actually belong here theoretically, but it's labeled as related to food because of the name. It actually relates to a satellite dish. So there are techniques in the system where you can kind of do this. You can remove stuff. You can move stuff around, and basically, if you refine the dictionary collaboratively, so the user will say, okay, so this is the wrong topic, and then kind of recompute. You go over this iterative process, then you can arrive at the refined representation, which is much better structured and much more discriminative. And you detect meaningful relationships between the actual topics. So the full system looks like this. We don't have to go over big details here. So you have this is your word cluster view. That this is what I would consider the main view of the system. And here you have various groupings and also detail windows that allow you to kind of debug the representation and then give user input to kind of refine and rearrange the topics to arrive at a better refined representation. So this has been an example of a system where you actually can target the representation itself. So lots of those systems take the representation for granted, but text analytics can be very helpful even in the context of building a representation. So to conclude, this is the overall taxonomy that we have followed in the lecture. We have gone over all the branches. So we have talked about the data. We have gone in great detail over the visualizations that we didn't know from the previous lecture. Domain is very important. Visualization tasks. We have discussed as well, and the analytic tasks are additional tasks on top of the classics that are relevant to the text data. Text is a very rich data type, which of course comes with its challenges. We need to process the data for meaningful visualization. We never visualize text raw. What is good is that simple techniques such as word counts and frequencies work very nice. The semantic text processing is still an open scientific challenge in information retrieval. It's a complete research community, so there's lots of opportunities in that regard. Text analytics approaches are usually custom, so there is no be-all end-all text analytics system, much like there is no be-all end-all visual analytics system. You always tailor it to the domain that it's relevant for, or for the tasks or the groups of tasks that you want to complete. and you can inspire yourself in the recommended literature on the website that I have linked towards the beginning of the lecture, and of course beyond. And one kind of meta note is that note how each paper is quite well explained by just looking at its figures. So that's a nice property of visual analytics / information visualization papers, is that if you actually read just the figures, then you should be able to get like at least 80% of the actual paper. So leverage this for reading and writing. So if you want to go into reading the papers, and you say, okay, this could be interesting to read, but I am a bit intimidated by reading scientific papers, then for this field you can do this. You can go over the figures. It can help you greatly. Okay, so that's the end of the lecture. Are there any questions?
Yeah, there's a question from Shores for the event queuing dashboard. I'm not sure what a frame means in this context.
Yes, so the frame is admittedly a bit confusing term that they have used. So basically, when you have an event and it's being reported in the media, then the communicators, so basically the authors of these reports, form a point of view that encourages a certain representation, and they can have various intents in doing this, or they can have no intent at all. So it can be conscious, subconscious. It can be meant well. It can be manipulative. And so basically, you're saying something like, I don't know, COVID came because of a bat being of an infected bat being eaten by a certain person in China, or it's somebody will say, okay, it's a deliberate attempt by someone, or it's being manipulated. So we can have conspiracy theories. Those are also sorts of frames, right? And these frames are and the event queuing is nice is used to detect and analyze these frames and the various parties / countries that are promoting these interpretations of events that are called frames. I mean, it is a bit of confusing terminology, and it doesn't help that the actual frames in the paper are very abstract as well. So they're not labeled something like COVID bat or COVID China, COVID US or something, but they're labeled, cause and problem threat, cause human, cause policy. So it's a bit of a tough term, but yeah, interpretation that's being pushed by someone, basically. Other questions?
All right, thanks. Yeah, Liansen asks, could you maybe give a concrete example of event detection and how it's done exactly?
Well, yeah. So basically, event detection is usually done by doing your semantic analysis. So I'm gonna give us semi-particular explanation, but going to all the way to the beginning of the lecture. It's gonna take a while. Yes. So here we have discussed that basically you do this entity extraction and topic analysis modeling, and event detection is basically doing this over time. So if you would do 9/11, let's say, so you're going to analyze a stream of text data, and then suddenly after September 11th, there's going to be something like there's going to be New York and World Trade Center and flights, terrorist attacks, Al-Qaeda, and suddenly these entities will start popping up in great frequencies with a very sharp start. So that's how we detect the event, basically. So then you're going to say, okay, so something happened, and usually you detect events, and then you have some sort of for let's say for the analytics purposes, for the semantics, you either go over it yourself as the data analyst. So you're going to say, okay, here is my list of events that the automatic techniques have detected. So suddenly a jump in some entity being prominent. Sometimes you take the approach of basically just detecting whatever you can and visualizing it. So then you let your user decide what an actual event is and what's not an event. Or you have some arbitrary threshold. So you're going to say, okay, it's only an event if I receive a word count of you know, or if I receive a story count of, you know, 20,000 per day. So those would be the methods of how to detect events in your data.
All right, thanks. Then he also asks, what technique can be used to discover patterns in temporal text data?
To detect patterns in temporal text data? Well, again, it's the same. So mostly what you do is you detect the topics and the entities that will form a graph, and then you kind of reduce the entire problem to the graph problem that we discussed last time, right? So you're going to see the evolution over time, and also the geotemporal visualization. So you're going to see. So if you, for example, can plot the entities or topics on a timeline using just a line graph, and you're going to see peaks. So is there a seasonal pattern? And you're going to use all these kind of plots and seasonality in temporal data, basically. Yeah, it is a pattern, for instance. But I mean, again, this is like the full detailed explanation is that this is information retrieval, right? So all of these things, I'm giving a very, very brief summary responses to all of these, because to answer everything in detail, I mean, this could be a lecture on its own, right? So how do you detect patterns in temporal text data? That's a very, very broad question. So NLTK should give you a good start if you're interested in these topics, and then it's for the full detail is delving into the field of information retrieval, I'm afraid. Yeah.
All right, thanks. I think that's all of questions for now.
Okay, very good. So thanks for coming to the lecture, and I'm going to see you tomorrow with multimedia analytics. See you.